Good evening, students. You're welcome to AAE 468 Advanced Orbital Mechanics video lecture 3. Today is let me check what today's date is. Today is the 19th of February 2015, and the time over here is 11:32. So, from our previous class, we started talking about from our previous classes. We started talking about orbits in 3 dimensions, and we went through the concept of the celestial sphere, and we talked about the right ascension and declination frame, and then we said, given the state vectors, we looked at the ways in which we could obtain the orbital elements, and then we noted that the 6 orbital elements that are quite often used are the specific angular momentum, the inclination, the right ascension of the ascending node, the eccentricity, the argument of the perigee, and then the true anomaly. And then we looked at the algorithm which could be used to calculate the orbital elements from some given state vector, that is the position vector and the velocity vector. And then we said we were going to start looking at how we can get the state vectors from known values of the orbital elements. And to do that, we need to look at coordinate transformation. If we consider 2 coordinate systems, 2 Cartesian coordinate systems, such as illustrated in figure 4.9, we look at an unprimed system with axis x, y, z, axis x, y, z, and then the prime system with axis x prime, y prime, and then the z prime. The unit vectors of the unprimed axis x, y, z are I kappa, j kappa, k kappa, and those for the primed system are I prime kappa, j prime kappa, and k prime kappa. Actually, maybe I should just for a while switch to the textbook, because the image seems to be sharper there. No. Okay. So we have 2 Cartesian coordinate systems. Let me try to go. So we have 2 Cartesian coordinate systems. We have the first one, which is the unprimed one. So we have the x, y, and z, and then the unit vector here is I, the unit vector there is j, and the new unit vector here is k. Oh, it's not showing, is it? Why isn't it showing? Okay, the light was too bright. And then, so this is for the unprimed system. And then we have some other one. So we have x prime, y prime, and then z prime. And the unit vector here is I cap prime, j cap prime, and then k cap prime. So we have two Cartesian coordinate systems with origin at the same point, but with some kind of differences in orientation to one another. So we are going to try to see how we can describe a vector oriented in one of the Cartesian coordinate system in the other Cartesian coordinate system. So that is what we are going to try to do. So we note that from vector analysis, the dot product of a vector by itself is equal to 1. So that means the dot product of the unit vectors of the unprimed system I dot I is equal to j dot j and is equal to k dot k, which is equal to 1. Since they are unit vectors, their magnitudes are equal to 1. So the dot product of a unit vector by itself is just equal to 1. And since they are also orthogonal, the dot product of a unit vector in one direction with another unit vector on the other direction is just going to be equal to 0, because technically the dot product just computes the reflection of one vector on the path of the other. But if they are orthogonal vectors, that means there is no way that one of the orthogonal vectors will have any reflection or component in the direction of the other. So that means that the dot product of orthogonal vectors, of course, the dot products are equal to 0. So similarly for the unprimed system, since the unit vectors in the unprimed system are also orthogonal, we have equation 4.16 and equation 4.17 for the dot products of the orthogonal vectors, and equation 4.16 for the dot product of a unit vector by itself. So from figure 4.9, that is this one, we can observe that the unit vectors of the prime system can be expressed in terms of their components in the unprimed system as follows in equation 4.8. And on the figure shows the graphical expression of this equation for the k axis. So we are just going to look at that. So looking at the k axis, if we want to express the unit vector in the z prime axis of the prime system in terms of its components in the x, y, z axis of the unprimed system, we see that k has its components on the x-axis to be on the x-axis of the unprimed system to be Q31, and then its component on the z-axis of the unprimed system is Q32, and it's Q33, and that's its component on the y-axis of the unprimed system is Q32. Please look at the figure well and get yourself comfortable with the figure. So I'm going to go again. K has a component on the x-axis, which is Q31, the x-axis of the unprimed system. And then on the y-axis of the unprimed system, it is Q32. And then on the z-axis of the unprimed system, it is Q33. That means we have K prime That means what we are saying now is we have K prime if we want to express K prime in terms of X, Y, and Z, we have to look at its components on this axis. And that's what has been denoted as Q31. And then we have to look at its components on the y-axis. And that's what has been denoted as Q32. Is it clear? Q32. And then we have to look at its components on the z-axis. And that's what has been denoted as Q33. So that we can write that K prime let me try to set this well. So that we can write that K prime is equal to Q31I plus Q32J plus Q33K. So we've successfully expressed K prime, that is the unit vector in the Z prime axis of the primed axis, in terms of its components in the X, Y, Z directions of the unprimed system. We can do a similar thing for J and I. I'll try that on your own. And then what we are going to arrive at is equation 4.18. You see that the third expression there is just what I've tried to explain. So try to get the expressions for I prime and J prime on your own. So you see where Q's in these expressions are just the direction cosines of the primed unit vectors, denoting projections of these vectors onto the X, Y, Z axis of the unprimed system. So similarly, the unprimed unit vectors may be resolved into components along the primed system to obtain a set of similar equations to equation 4.18 as follows in equation 4.19. So if I just quickly shift to the webcam. So we are going to try to do it for K. That is, we are going to try to resolve K into its components in the unprimed system. That is K, its components in Y, J prime, its components in I prime, and then its components in K prime. So actually it's quite hard to view now. Yeah, we just go through a similar process to get the components of K. The components of K, that is K in the unprimed system, in terms of its projections onto the primed system. In order to save time, I won't try to figure out how to exactly go about this, but it's just resolution of the unit vectors. So if we now substitute equation 4.20 into 4.14, this is 4.20. That is the resolution of the unit vectors of the unprimed system into components in the. Oh, sorry, I've skipped something. So we have equation 4.19 However, we note that I prime dot I equals I dot I prime. That is, if you dot I there, I prime there in equation 4.18 with I in equation 4.19, you see that they end up being the same. So that from equations 4.18, this and 4.19, we find that Q11 is equal to Q11 prime. And likewise, if we do I prime dot J, we will find that it's equal to J dot I prime. So similarly, we'll be able to see that Q12, when you try that, I urge you to try it on your own, you'll be able to see that Q12 equals Q21 prime. If we proceed in that fashion, it will be clear that the cosines in equation 4.18 we'll be able to express them in terms of those in equations 4.19, so that equation 4.19 may be written in the manner it is in equation 4.20. That is, we are expressing the unit vectors in the unprimed system in terms of their projections on the primed system. So if we substitute equation 4.20 into equations 4.14, this is 4.14. That is, if we perform the dot operation of the vectors, the unit vectors by themselves, we will get to see that we have the dot product of I by itself to be equal to 1, giving us the fact that Q11 squared plus Q21 squared plus Q31 squared equals 1. Similar expressions go for J dot J and then K dot K. Then we proceed further. If we substitute equation 4.20, still this same equation 4.20, if we substitute it into equation 4.15, equation 4.15 there, and making use of equations 4.16 and 4.16 this and 4.17, we obtain the three expressions that I dot J, since we are crossing two orthogonal unit vectors, since we are dotting two orthogonal unit vectors, the result is equal to 0. That means the addition of the products of these projections of the vectors on themselves will be equal to 0. So we have this to be true, that to be true, and that to be true. So if we let Q represent the matrix of direction cosines of I prime, J prime, K prime relative to I, J, K as given in equation 4.19, then we can directly write that Q in matrix form is just has the elements Q11, Q12, Q13, Q21, Q22, Q23, and so on, which is just equal to I prime dot I prime dot J, and so on. So the transpose of the matrix Q denoted by Q transpose is obtained by interchanging the rows, of course, and columns of Q. Thus, we have the Q transpose to be given in equation 4.24. So we can form the product of the transpose of Q with Q. When we do that, we get the matrix over here. So before we move forward, we can directly recognize the first row here to be equal to 1 if we look back to equation 4.21. So that's the first row there, that's 1. And we'll see that when we look through that the product of the matrix Q and its own transpose. When we look at the elements in that product, you recognize this to be 1, that to be 1, and this also to be 1. So over there in the diagonal, 1, 1, 1. And then these other ones from here are equal to 0 from equation 4.22. So we have 1, 1, 1, and then 0, 0, 0, 0, 0, 0. That means the product of the transpose of Q and Q is just equal to an identity matrix. An identity matrix. So in a similar fashion, we can substitute equations 4.18, this equation 4.18, this, into equations in a similar fashion, we can substitute equations 4.118 to equations 4.16 and 4.17 and make use of equations 4.14 and 4.15 to obtain a similar result as in equation 4.25, that is equation 4.26. So since Q satisfies equations 4.25 and 4.26, it is called an orthogonal matrix. So if we let the vector V be expressed in terms of its components in the unprimed system, so V has a component in the x direction, Vx, a component in the y direction, Vy, and some component in the z direction, Vz. And along, if we can also express the same vector in terms of its components in the primed system. So given as shown on the slide there, the two expressions of course must be equivalent because we are talking about the same vector. And a vector, the expression of the vector is independent of the coordinate system used to describe it. So the two expressions there must be equal. So that's why we have equation 4.27. If you now substitute equations 4.20 into the right hand side of equation 4.27, that is if you try to express I, J, K in terms of their components in the prime system. I'll quickly go back to 4.20 so that you see the equations I'm talking about. So these equations, so we are trying to express I, J, K in the unprimed system in terms of their components in the primed system. So if we substitute those equations into equation 4.27, the right hand side of equation 4.27, we can do some more algebra by collecting the like terms which we get. And then we have this equation here. We can go further to now see that Vx prime must be equal to the expression here, because I prime is equal to I prime, J prime is equal to J prime, and K prime is equal to K prime. Therefore, the Vx prime must be equal to that, Vy prime must be equal to this, and then Vz prime must be equal to this as well. So, and that is just equation 4.28. So in matrix form, we can write it as V prime, that is putting this as a column matrix, and then noting that Q is just Q11, Q12, Q13, that is a 3 by 3 matrix. And then V is just Vx, Vy, Vz, a column matrix. That means we can express equations 4.28 in matrix notation, in which we now have it to be equation 4.29. So equation what we just done now shows how to transform the components of the vector in an unprimed system into its components in the prime system. The inverse transformation from prime to unprime is found by multiplying equation 4.29 through by the transpose of Q. When we do that, we have this. That is the transpose of Q times the column matrix of the vector expressed in the unprimed system in the prime system is equal to the expression here. Or we've noted already that the product of the transpose of Q and Q is equal to the identity matrix, which is 1. So essentially what we are saying is that V is equal to Q transpose times V prime. That means when we want to go from the prime system to the unprimed system, we just have to multiply, do the product of the vector expressed in the prime system by the transpose of the direction cosine matrix. So we now look at the coordinate transformation when there is just the rotation about a single axis. And then to do that, we consider the case where the coordinate transformation involves rotation about the x-axis as shown in figure 4.11. That means we are just the transformation we are going to be looking about is just for the rotation about x-axis. That means the I, the unit vector of the in the x direction for the prime and the unprimed system are coincident. That means I equals I. If I switch to the, let me quickly draw this down so I can switch to the webcam. Okay. So what we are going to try to do now is to express I prime in terms of its components in the XYZ axis of the unprimed system. So for I prime, note that it's equal to, it is fully coincident with I in the unprimed system. So we have 1 I plus, it doesn't have any components on the J axis, that is the Y axis of the unprimed system. That is 0J, and it doesn't have any components in the K axis, that is the Z axis of the unprimed system, so plus 0K. So we go further to J prime. This is J prime here. If we look, because we've rotated the prime system through an angle phi about the x-axis there, so the J axis of the primed system has been rotated from where it was through some angle phi, the angle of rotation. That means the component of J prime on the J axis of the unprimed system is just equal to, so if we start by noting its components on the I axis, you see that it is not, it is in the, this is X, Y, Z. So it's in the Z, Y plane. So it doesn't have any component in the X, Y plane. So that is 0, 0I. Then the component, its component in the Y axis of the unprimed system is just equal to cos phi, cos of the angle of rotation. So we have cos phi J and plus its component in the Z axis of the unprimed system is just the sine of this angle, the sine of this angle of rotation. So that's sine phi K. And then when we look at K prime, we see that it's equal to, it also doesn't have any components in the X axis of the unprimed system. So we have 0I. Then looking at, when we rotated about the X axis, we just moved K from where it was, coincident with the Z axis of the unprimed system before rotation. Now it has moved through some angle phi. So its component on the its component on the Z axis, sorry, its component on the Y axis of the unprimed system is just going to be the sine of this angle that is here. It's on the negative Y. That means it's going to be negative sine phi, negative sine phi J. Then its component on the Z axis of the unprimed system is just cos phi, so plus cos phi. We can now write this in matrix notation, having it to be equal to I prime, J prime, K prime is equal to 1, 0, 0, 0, 0 cos phi sine phi minus sine phi cos phi into I J K. That means if we are going, when we rotate about the X axis through some angle phi, this is the directional cosine matrix that we arrived at. So going back to the slide, that is how come we have the matrix here. So the same can also be done for the rest of the axis. That is, if we rotate about the J axis or if we rotate about the K axis, and those are presented on the next slide. So, but before we go on, we need to know that the transformation from, just like I said, the transformation from the XYZ coordinate system to the X, Y prime, Z prime system having a common x-axis is given by the matrix coefficient of the unit vectors on the right. So since it is a rotation through the angle phi about the x-axis, such rotation is denoted by R1 phi, in which the subscript 1 stands for axis 1, that is the x-axis, so that we can write the matrix coefficient of that rotation to be R1 phi equals this direction cosine matrix denoted by equation 4.32. So for in a similar fashion, we get the direction cosine matrix for rotation about the y-axis there in a similar fashion, and then the matrix of the rotation about the y-axis is axis 2, so R2 phi is equal to this as given in equation 4.33, and also the same can also be obtained for the rotation about the z-axis. So that means the k prime and the unit vector in the unprime system and then the unit vector in the prime system are coincident along the same line. We are just rotating about the z-axis. So in a similar fashion to what we did for the rotation about the x-axis, the rotation about the z-axis produces this direction cosine matrix. So, and then it is denoted by R3 phi equals this. So the transformation between two Cartesian coordinate systems can be broken down into a sequence of two-dimensional rotations using the matrices R, I, phi, where I is just equal to 1, 2, 3, depending on which of the axes you are talking about. 1, of course, denotes X, 2 denotes Y, and then 3 denotes Z. We will be using this for the transformation of transformation of the state vectors from equatorial plane to the perifocal frame, or vice versa. So if we quickly take a recall on what the perifocal frame is, we said in AAE 313, we said the perifocal frame is a natural frame of an orbit, and its center is just at the focus of the orbit. And then the unit vector in the angular momentum vector direction is denoted by W kappa, and of course it's given by equation 2.106. And then in the perifocal frame of reference, the state vector R is given by x bar p, that is there, its components in the p kappa direction, and then its components in the q kappa direction. So it's given by equation 2.107. The velocity vector is also given by equation 2.110. So we note that x bar is r cos theta. So if theta is a true anomaly, at any point in time you can find the x component of r, that is it's r cos theta, and then the y component is r sin theta. And the magnitude of the position vector, of course, is given by the orbit equation, that is Kepler's first law expressed in mathematics. So that equations 2.107 and 2.110 can be written as equation 2.109, and then that equation 2.109 for the position vector, and then equation 2.115 for the velocity vector. So in matrix notation, equations 2.109 and 2.115 can be written in this manner. That is the magnitude times the Coulomb vector, which gives the direction we are talking about. There is the x bar direction, y bar direction, and since the orbit is just described in the orbital plane, you don't have any component of r in the direction normal to the orbital plane. So the subscript there, X bar, denotes that we are talking about the perifocal frame, as opposed to when we might be talking about the position vector in the equatorial, geocentric equatorial plane. In such case, it would be denoted as Rx, more with the bar. When you say Rx bar, you are talking about the position vector in the perifocal frame. And this equation 4.38 is the velocity vector in the perifocal frame. So figure 4.14 illustrates the relationship between the perifocal and geocentric equatorial frames. So we move on. The transformation from the geocentric equatorial frame into the perifocal frame may be accomplished by the sequence of 3 rotations, as illustrated in figure 4.15. We are going to look at each of the rotations individually so that we won't get confused here. The first rotation is through the right ascension. That means through the right ascension from the node line. So the right ascension is denoted by capital omega. So that means we are rotating about the z axis of the equatorial plane, and that's why an eye has been drawn above the z axis to show that that is where we are keeping constant, and then the rotation is now about that axis. And then the second rotation is taking about the node line of the ascending node, and it will be through the inclination of the orbital plane, and then the third rotation is through the angular momentum vector direction, and it will be through the arguments of the perigee. So we are going to look at the individual rotations one by one on the next slide. So rotation 1 is around the z axis. So now we are just looking at the z axis. When we are looking directly overhead to the z axis, this is what you see. So z axis is just there at that point, and we are rotating in the counterclockwise direction through the right ascension. So right ascension is omega. By the time we are rotating, by the time we rotate the vector from there to I prime, then the j unit vector will have rotated from j prime. It's from j to j prime as well. So what we just need to do now is to now use the R matrices that we got a while ago, and then we just have to note that since we are rotating about the z axis, we put R3, and then omega is now replacing phi, since omega is the angle we are rotating, the angle of rotation. So we just put omega into the these equations which we got. Right? This is R3 omega now. So omega there, omega there, omega there, omega there. And then we move on to the rotation about the node line, the x-axis. The x-axis of the equatorial plane through the inclination. So now the x-axis of the equatorial plane, that is the node line. So because we are moving about the node line, it's just situated there, and we are moving through the angle of inclination. So by the time we move from J prime to J prime prime, the vector would have moved from K to W kappa, and we are just going to use the direction cosine matrix for rotation that we got before. And because we are moving about I is on the x-axis, we have R1, and then I is the angle we are moving, the angle of our rotation. So we have the direction, the rotation matrix for rotation about the x-axis will be given by equation 4.40. And then rotation 3 is around the angular momentum vector axis of the orbital plane. So, and it is through the argument of the perigee, omega, the small omega. So it is just in the same manner as we did for the previous ones, and then the orthogonal transformation matrix associated with this rotation is given in equation 4.41. And since we are rotating about the W, about the, if you like, you can call it the z-axis of the orbital plane of the perifocal frame. That is why we have R3 there, and then small omega is the angle of rotation, and that's why small omega is in the orthogonal transformation matrix. So finally, let us note that the transformation matrix from the equatorial plane to perifocal frame, that is Q, X, big X, small x bar, is just the product of the three rotation matrices given by equations 4.39, 4.40, and 4.41. That is equation 4.42. That is, we are just combining the aggregate result of rotations about the z-axis of the equatorial plane, the node line of the orbit, and then the angular momentum vector direction of the orbit. So if we substitute the three matrices on the right and we carry out the matrix multiplication, we have Qx, big X, small x bar to be equal to equation 4.43. And then we have to remember that it is an orthogonal matrix, so that for the transformation from the perifocal frame to the equatorial frame, we have Qx, small x bar x is just equal to the transpose of equation 4.43, and that is what we have in equation 4.44. So that the components of the state vector are given in the geocentric equatorial frame as R with components x, y, z, and then velocity v, the velocity vector given in terms of its components in the x, y, z plane. The components in the perifocal frame can be found by just multiplying the position vector in the geocentric equatorial plane by the transformation matrix, the direction cosine matrix, and then the same can be done for the velocity vector too. And then if we have the state vectors in the perifocal frame, we can also get the state vectors in the geocentric equatorial frame by just multiplying the state vectors in perifocal frame by the inverse of the transformation matrix from equation 4.45. So we have a way now to get the state vectors given the orbital elements. The orbital, when we have the orbital elements, it will be in the perifocal frame. That means we have a way to get the state vectors expressed in the equatorial geocentric frame with the knowledge of the orbital elements as expressed, of course, always expressed in the perifocal frame. So the next thing we'll be looking at in the next video lecture is the effect of the Earth's oblateness on the motion of satellites. But before we finish this lecture, let's just look at some example of the use of the direction matrices from textbook. So this is example 4.4. In figure 4.10, this is a figure here, 4.10. The x prime axis is defined by the line segment O prime P, O prime P. So that's the x prime axis, and the x prime y prime plane is defined by the intersecting line segments O prime P and O prime Q. So that's the x prime y prime plane. The z prime axis is normal to the plane of OP and OQ, and obtained by rotating OP towards OQ. So rotating the rotation of this vector into OQ gives an orthogonal vector to their plane. Using the right hand rule, find the transformation matrix Q B if there's a vector given by this. Find the vector in the primed axis. See if you have a vector in the primed axis, find the vector in the unprimed axis. So in order to find a transformation matrix, we are going to resolve the directed line segments O prime P and then O prime Q into components along the unprimed system. Since we have the coordinates of the starting point of the line and then the end point of the line, we are just going to, in order to get it in, and the coordinates are referenced to the x, y, z axis of the unprimed system. So what we just do then is to do -5, -3 for the component on the x-axis of the unprimed system, and that's why we have -5, -3 there. And then for its components in the y-axis of the unprimed system, we have 5 -1, and then the same for k, you have 4 -2, 4 -2. So that is OP in terms of x, x, y, z of the unprimed system is this. And then in a similar fashion, we can get OQ to be equal to this in terms of its components in the unprimed axis. So taking the cross product of OP and OQ, if we take the cross product of OP and OQ, we get a vector in this axis, that is in an axis which is perpendicular to the plane defined by OP and OQ. So we have So the cross product of OP and OQ yields a vector Z prime which lies in the direction of the desired positive Z prime axis. So the cross product of OP and OQ gives this vector, and then taking the cross product of Z prime, this vector, into OP, then gives a vector Y prime which points in the positive Y direction. That is, if Z prime is a vector here, so if we take the cross product of Z prime and then OP, obviously we have a vector in the direction of J prime. So Y prime, which is the vector in the direction of J prime, is equal to the cross product of Z and OP, and it's given by that. So if we normalize the vectors OP, Y, and Z, we can get the unit vectors in their directions, I prime, J prime, and K prime. So we just have to do I prime equals the vector divided by its magnitude, vector OP divided by its magnitude. So we have I prime to be equal to that. Then J prime, we have it to be equal to that, and K prime, we have it to be equal to that. So that the components of I prime, J prime, and K prime are the rows of the orthogonal transformation matrix Q. Thus, Q is equal to this minus 0.8729. We just have to bring all these components into the matrix. So that is Q. So, and that's for the first part of the question. Then the second part says you have a vector expressed by its components in the unprimed system, and we want to find it in the prime system. So we have the transformation matrix. All we have to just do is to do the product of the transformation matrix and the vector. So we have V prime then. So, and then the third part of the question says we should find the vector in the unprimed axis given its value in the primed axis. So what we do again is to just multiply by the transpose of the transformation matrix, and then we have the vector. So it is quite straightforward. If there is anything you haven't got right now, just take your time and watch over the video again. And if there's still something that you're not clear with, put the questions down, send me an email, or wait till we have the answer question and answer session, and we'll try to figure out what the we'll try to figure out a solution to the problem. Remember, as always, always find a way to send me your feedbacks, comments, and of course questions. Thank you. So we will so we'll be starting from the effects of the edge oblateness in the next video lecture.